Okay, so then as a important review type of question, I'd like to do the following. If f of x comma y, so this is not a vector field. There's not a capital F, there's no arrow on this. So this is just a function with multiple input variables. So it's defined to be 3x squared minus xy plus 2xy squared minus 5y. Then I'd like to find the gradient of f. We've seen this task before. So gradient of f, we just need to find, so we end up with a vector, and the first component should be f sub x, right? Partial derivative with respect to x, so that'll be 6x minus y plus 2y squared. And then the second component is f sub y, so it's, partial derivative of f with respect to y, and that's going to be negative x plus 4x minus 5, angle bracket. Okay, so here's the thing. This here, the gradient of f, or really more correctly, gradient of f of x comma y, it's actually a vector field. It is a vector field. Perhaps early in the semester, informally, we just called this thing a vector function because, of course, it is a function where the output is a vector. But because the input, there's more than one. It's not just an input called t or just an input called x. There's an input x and an input y. Two input variables, this thing should truly have been called a vector field even way back when, but that would have just added unnecessary confusion. Yeah. So let's just in fact name this vector field here just with a capital F arrow right now. So capital F arrow is 6x minus y, plus 2y squared, comma, negative x plus 4x minus 5, finish angle bracket. So this is a vector field. So a thing that we had learned a long time ago, just taking a function with multiple input variables and finding its gradient, that was already a vector field way back when anyway. Okay. Now here's the thing: if a vector field is obtained from computing the gradient, then this is called a gradient field. So we have right here an example here of something that is technically a gradient field. Okay, so definition, we've already introduced it by example, but let's just say this. So if there exists a function f, lowercase f, such that vector capital F equals gradient of lowercase f, then the vector field capital F arrow is called conservative. And if that happens, then little f is called a potential function of capital F arrow. Okay, there's the definition. This is a very, 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 very important definition for us. So, example. It's really the example we looked at, but I just want to put the right language to it. So capital F of x comma y equals, angle bracket, 6x minus y plus 2y squared, comma, 3x minus 5. Oh, it's not the same example. New example. That's fine. Okay, this is a conservative vector field. So not just any old vector field. This vector field we're introducing is a conservative vector field. Why? It's because of this. Because the function lowercase f of x comma y equals 3x squared minus xy plus 2xy squared minus 5y is a potential function. For or of capital F arrow. So take this, if you were to take what I just circled here, compute the gradient, so find partial with respect to x, partial with respect to y, you should be getting that vector right there. Okay, the analogy, I know that the language is all a little strange, but you'll be all right. So here's the thing. There's something from Calc 1 that serves as a really good analogy to what's going on. So back in original type of function land, you know, f of x equals x to the fifth, f prime of x equals 5x to the fourth, and we let capital F of x equal 5x to the fourth. So very often the result of derivative has been called capital F back at a time when you looked at the fundamental theorem of calculus. And here's the kind of language we use. We say that capital F of x equals 5x to the fourth. If you're starting with this thing first, we say that this has an antiderivative. And specifically, little f of x equals x to the fifth is an antiderivative of capital F here. Right? So this is, I think, a useful analogy to what we're seeing going on. Okay, question. Let f of x comma y comma z equal xy plus y times sine of z. So what is the gradient of f? Conclude that a certain gradient field is a conservative vector field. Okay, answer. So I think this will be a good computation to help. The computation itself is not bad, but doing the computation and practicing the language I think will be extremely important here. So let's compute the gradient. Yeah, so partial with respect to x first, so y. I think that's it. Yeah, okay. Partial with respect to y, so x plus sine of z. And then the partial with respect to z, first term differentiates to 0 with respect to z. We just get y cosine of z. Okay, so cool. This is the gradient of f. We're done up to there. Now, conclude that a certain gradient field is a conservative vector field. So if we just took this thingy here and said, hey, that's a vector field, let's just define it with a new letter, capital F, arrow, of x comma y comma z equals bracket y comma x plus sine of z comma y times cosine of z, close angle bracket. This is an example of a conservative vector field. We're done. This is a conservative vector field. Why? Because by definition, a conservative vector field is one that just happens to be equal to the gradient of some function, and it's the gradient of this function.